上周我完整的读了一篇 Transformer 最佳化的综合型论文，名字是《A Survey: Collaborative Hardware and Software Design in the Era of Large Language Models》。里面提到了很多加速技术，但其中 KV Cache 这个部分让我觉得特别有趣，也值得深入了解。加上上周院长的报告，让我对 KV Cache 有了初步的概念。所以这周特别挑了一篇相关的研究，想了解在实作上如何对 KV Cache 进行优化。我这周阅读的论文是这篇 Reducing Transformer Key Value Cache Size with Cross-Layer Attention。那接下来我就会介绍这篇论文的内容。So when decoding long sequences, transformer you use past tokens representation instead of recomputing them each time. These stored tensors, the KV cache, accelerates inference but consume huge memory. As sequence length of the batch size grows, the cache becomes a serious bottleneck. Prior work tackled this by modifying attention structure, multi-query, and group query attention. In the original transformers, each attention head has its own key and values, so we need to store many KV pairs. Shaza proposed multi-query attention, which is MQA, where all queries share a single KV head, dramatically cutting memory. Later, Ainsal et al. Generalized the idea to group query attention, letting designers balance between efficiency and accuracy. Even though MQA and GQA reduce KV size within layer, they still require separate KV caches for every transformer layers. The author noticed that attention maps between nearby layers are often similar, so why not sharing KV across layer too? So the core idea is simple. Extend the sharing dimension from across head to across layers. In cross-layer attention, we will say CLA in short for the later presentation. Not every layer computes its own KV projections. Some layers reuse the KV from the earlier ones. This cuts the cache size roughly in half, and the team shows it barely hurts accuracy. In CLA2, each pair of layers use one shared KV. If you visualize the transformer stack, instead of 10 layers each storing their own cache, only 5 needs unique KV caches. This reduces memory use by about half. It's an plug and play design. Works with MQA, GQA, they're orthogonal, and standard distributed setups. So these two figures show how cross-layer attention changes the transformer architecture and KV cache layouts. In the traditional transformer here, every layer has its own key and value projection. So each layer stores its own KV cache. It's very memory heavy. And CLA removes that redundancy. Only some layers computes K and B. The next layer reuses them. In CLA2, um, this figure is for CLA2. Each Every two consecutive layers share one KV cache. In CLA3, three layers shared one. This simple change cuts KV cache memory roughly by the sharing factor, about 2 times smaller for CLA2 with almost no accuracy loss. So the main idea, share KV cache across layers instead of recomputing them, letting the model keeps the same expressive power while using much less memory. CLA mainly saves memory, not compute. Since fewer KV projections exist, parameters and flops drops a bit, but each decoding step still reads KV from the memory. The big benefit is enabling larger batch size and longer context under the same GPU memory. To test the design cleanly, the author trained their own models at 1B and 3B scales using the Slim Pajama dataset, following Llama-style architecture. They compare CLA configurations against standard MHA, GQA, and MQA to plot memory versus accuracy trade-offs. At 1B scale, CLA2 consistently shifted the Pareto frontier, same accuracy for half the memory. Using larger sharing factors like 3 or 4 made the models less accurate, suggesting that the adjacent layers are similar, but not too similar to share across many levels. At 3B scale, CLA2 remains effective, even outperforming the MQA baseline in perplexity while using half the KV memory. This shows the approach scales and is robust to train hyperparameters. Here's a big picture overview. So CLA stacks with existing attention compression. If you start from multi-query, you get about 16 times reduction over MHA, and CLA doubles that again. So, so roughly 32 times smaller KV cache compared to the original transformer with very little accuracy loss. The study concludes that sharing KV cross adjacent layer is a low risk, high reward tweak. The recommended recipe is CLA2 plus MQA. Cut KV memory by half with little or no accuracy loss. This makes longer context or smaller memory inference feasible, especially useful for edge devices. The author reinforced system-level benchmarking to future work, but CLA could pair well with token pruning or quantization. It's a building block for efficient inference, perfect for resource-limited or edge environments. And this is the reference. Thank you.